some review problems at the end of Chapter 4 here. And maybe before we start them, we just take a quick thinking break about what is it that we did in Chapter 4. I think you could think about it productively, helpfully, as a three-part thing that we did. The first part is just understanding 2D vectors, and in particular the like the motion vectors, or the position, velocity, and acceleration. Understanding how to work with the i's and the j's, and how to do like, oh, the velocity is the derivative of this, how to find average, like that average acceleration, for example, that we found in number 68 in the assignment immediately preceding this one. So all that vector kind of stuff. That set the stage for us, and then in particular we were interested in two special kinds of two-dimensional motion. It was projectile motion and, of course, in projectile motion, the horizontal part is constant velocity and the vertical part is constant acceleration of 9.8 meters per second in the down direction. And then also uniform circular motion. And that has its own special things, where the magical acceleration is of a magnitude v squared over r, and it's pointing toward the center of the circle. A couple other equations that go with that. So that's what's up with Chapter 4. That's what it all focused on. You could imagine a physics teacher even designing a test that had maybe, I don't know, say 3 free response questions that focused on each one of those things. I mean, it seems like one way of approaching it, anyway. Yeah. I think it's a very manageable chapter. Helps to just, I think, take a step back and think about what we did and try to organize your thoughts in that way. All right, so what do we have here? Your physics teacher picked out some problems that are going to touch on these different things, I suppose. So the first one, it comes from this section that's about average velocity and instantaneous velocity. So I guess that would be like a problem of this kind of thing. We have a plane that's flying 483 kilometers east. In 45 minutes. And then 966 kilometers south in 1.5 hours. For the total trip, what are the magnitude, direction of the plane's displacement, and the magnitude and direction of its average velocity and its average speed? Okay, so let's see. The displacement going to be this. So the displacement is, if we thought about this as I and j, say that displacement vector is just 483I minus 966j kilometers, and the magnitude of it is the Pythagorization, that's the noun form of that, the Pythagorization of 483 and 966. That's about 1,080 kilometers. They would like to know for part B the direction of that. So to do that, I will tangent invertize 966 483, so I'm just doing the tangent inverse of rise over run, 966 over 483, always ditching any negative signs for this, and make sure that I am in degree mode. I am. That's about 63.4 degrees, but where? Well, it's talking about the displacement, and this is a north, south, east, west problem, so this is south of east. Part C, they want the magnitude, C and D is magnitude and direction of the average velocity. Well, average velocity is displacement over time, and I've got the displacement vector right there, so I just have to divide that by the time. And I suppose we want to do it in kilometers per hour, so this is 3/4 of an hour. So that's going to be 483I minus 966J kilometers over 2¼ hours. And I could go through that whole process, but of course the magnitude of this, if I divide this by the 2.25 hours, that's going to give me the right magnitude. So I'm going to do that. The magnitude is 480 kilometers per hour. And the direction, well, the direction of the displacement and the direction of the average velocity, if you take the displacement and divide it by something, there is actually no defined operation for vector division. There's a couple ways of multiplying vectors that we'll come across later in the year. So dividing it by what's called a scalar, something that does not have direction, like time, does not change the direction. So it's exactly the same direction as this. All right. Direction of displacement and average velocity over the same time interval, of course, are always the same. That is always going to be true. And then last part, what's its average speed? Well, that's different. Average speed is total distance. Don't care about direction over time. And the total distance here is 483 plus 966. 483 plus 966 over the 2¼ hours. All right. That is a good little review of some of that stuff from early in the chapter, I think. Number 16, we've got, this is from the section called Average Acceleration and Instantaneous Acceleration. So let's see how we do here. Velocity v of a particle moving in the xy plane is given by this vector function, 6t minus 4t squared in the I direction, plus 8j. All right. Since, let's see, what's the acceleration when time is 3? So if this is the velocity, the acceleration is the derivative of this, and we just do the derivative by components. So this would be 6 minus 8t in the I direction. And then this is a constant, so the derivative of that is 0. We could write that there for emphasis if you want. That's meters per second. This is meters per second squared. And they would like to know for part A, what's the acceleration when time is 3? So the acceleration at time 3 is equal to 6 minus 24. Dang it. My I came out like a J. And then I'll just put the plus 0J in there for good luck. Right? So that's that. And for part B, what are the... Oops, sorry, I'm looking at the wrong problem there. When, if ever, is the acceleration equal to 0? Well, for the acceleration to be 0, if they just say the acceleration is 0, that means the magnitude is 0, which means both components have to be 0. Well, this is always 0. So is that ever equal to 0? Sure. That's equal to 0 at t is equal to 0.75 seconds. So that's the answer for that. When, if ever, is the velocity 0? Well, the velocity is never 0 because for the velocity to be 0, to have a magnitude of 0, both of the parts would have to be 0. If you think about how we find that magnitude of the velocity, we're Pythagorizing two numbers. And if you want to get 0 out of that, they both have to be 0. So that's never going to happen because it has a constant j component here that's never going to be 0. Never. When, if ever, does the speed equal 10? Well, what's the speed? The speed is equal to the magnitude of the velocity. So that's the Pythagorized version of these things. So that's 6t minus 4t squared plus 64. So the speed, and they want to know, is that ever equal to 10? So maybe. Could just have to do some algebra, I guess. So squaring both sides of this, 6t minus 4t squared plus 64 is equal to 100. So I guess that could be plus or minus 6, couldn't it? So let's see what we have here. I think I'm going to go ahead and solve this version of this equation. Physics is always calculator allowed, so why not? So how do you solve an equation like this? There's different ways of doing it. I prefer the get everything on one side and graph that and then look for the zeros. You could also graph this and graph this constant here and see where they intersect. Of course, you have to tweak your window to make sure you can see everything you need to see. So I'm going to do this version. I'm going to do 6x minus 4x squared minus 36, and then I want to know when that's equal to 0. So if I hit graph and look for the zeros, but not just going to hit graph. Let's think for a second here. My x's are times, so I don't need any times that are negative. And how high up on the axis should I go? Well, I could try going to 10. I could see here. Once I get to 10, then this would be like 60 and then 4 times. So this is way bigger, so I think 10 is plenty big for us to see when that might be equal to 6. And I only need to see in the y-axis. I only need to see where it crosses, so I could just go like, you know, -1 and 1. There, could do that. So let's see. Okay, there's a spot. And let's find that 0. Second, calculate 0. I'm not going to play the cursor game, especially because that's so steep. I can see clearly that it is between 2 and 3. So 2 is my left bound, 3 is my right bound, and let's find that. So at time is equal to 2.18 seconds. That is what we're looking for. Good. I'm never really sure how much experience you all have, my students here at Rockbridge County High School, with using your calculators to solve problems in the manner that I just did there. So I don't know, if you feel like you need a little bit of practice or a little more help with that, you let me know. I can make that happen. Uh-oh. 28. I feel like we've done this problem already. Did I already assign this somewhere? Yep. 24 to 30 even. That would include number 28. Well, what shall we do? Do want you to have practice with projectile motion. Did we do 32? Let's do 32 instead. You could do 28. Go back and review that. That's a good one. Now I'm going to substitute out number 28 for 32. So if you're just seeing that now for the first time, I'll try to make a note in Google Classroom somewhere that you should do the same thing. Or maybe I'll just go in and change the pacing guide. That would work. That would do it. So if you're just seeing that for the first time, pause here and please try to do this problem. You throw a ball toward a wall at a speed of 25 meters per second and an angle of 40 degrees. So that's, we're going to have to break this into its components. Sorry, those squiggly lines are supposed to be dotted lines. And that's 25 meters per second. So let's just crank these out here. It's got 25 cosine 40. And 25 sine 40. Okay. The wall is 22 meters from the release point. So we're throwing it at a wall that is 22 meters away. That seems like a delta x kind of thing, doesn't it? How far above the release point does the ball hit the wall? Okay, so let's see. If I set up my vertical and horizontal business, let's see what we know. Acceleration, of course, is negative g, negative 9.8 meters per second squared. My initial velocity in the vertical direction is 16.1. Don't know my final velocity in the vertical direction. I don't think that matters. And time, don't know. And delta y, don't know. But I think delta y is what I want, right? How high up does it hit the wall? So, well, I'm going to need something else here because I've only got two things and I need three. So here in the horizontal direction, I do know the delta x. It's 22 meters. And I also know my constant horizontal velocity is 19.2. So it looks like I can find the time here. So delta x is equal to velocity times time, because it's constant velocity, only one equation to relate these three things. So the time would be equal to delta x over Vx, which is 22 over 19.2. So it looks like our time is going to be 1.15 seconds. And I can borrow that and import that over to here. And then I can find my delta y. So delta y is equal to 1/2 at squared plus vit, which here is going to be negative 4.9 times 1.15 squared plus 16.1 times 1.15. Let's see what we get there. About 12 meters for that number 32. What do they want? What more do they want from us? What are the horizontal and vertical components of its velocity as it hits the wall? Horizontal and vertical? Well, the horizontal component of its velocity is constant. It's always 19.2. Constant horizontal velocity. And for part C, how about the vertical? Well, I know that final velocity is equal to acceleration times time plus initial velocity, so that is going to be negative 9.8, 1.15 plus 16.1. So it looks like the vertical component is going to be 4.83. That's the vertical component when it hits the wall, right? So it's still going up when it hits the wall. Of course, it's going forward with that same constant velocity. Now, let's see. One more part. When it hits, has it passed the highest point on its trajectory? No, because this is still positive. It's still going up. Still going up. All right, that was a good substitution, I think, for 28. Sorry about the confusion there, if there was any for you. And 38. A golf ball is struck at ground level. The speed of the golf ball is a function of time. The speed of it is given in this graph. The speed of it, now remember the speed is the Pythagorized horizontal and vertical, Vy plus Vx. That's how you find speed. And if we're talking about projectile motion, I mean, this is always true, but in the special case of projectile motion, this is a constant, and this is has that acceleration of negative 9.8 meters per second squared, taking down to be the negative direction. So the speed is given in this graph, and the scaling of the graph goes from 19 to 31 meters per second. Let's do a little squiggle there. So it bottoms out there and looks sort of parabolic, but that is not a parabola. And this low point right here happens at 2.5 seconds. How far does the golf ball travel horizontally before returning to ground level? What's the maximum height above the ground? All right. So, how do we do this? Well, there's one kind of key realization that you have to have here, I think, to be able to successfully do this problem. And I'm going to tell you what it is, and if you didn't get it, I want you to pause when I tell you what that thing is, because you will be able to finish the problem from there. I'm very confident. So the thing that you need to realize is at this low point right here, when the speed bottoms out, this is the peak. Now, how do I know that? Because when the golf ball is doing its trajectory like this. At all of these points, you're going to have a horizontal component and a vertical component of the velocity, except for right here at the peak where it's only horizontal. Right there, it's the only place where the velocity is horizontal, right? It's the only place where that horizontal tangent line to the path happens. So what that means is the speed, if you're Pythagorizing these, it's going to bottom out when this is 0, right, at the peak. This is constant, so this is not changing. You're always going to be adding something, doesn't matter whether it's positive or negative, you're squaring it. So you're always adding something to make this bigger, except at the very top when the Vy is 0. So what that means is the constant horizontal velocity is 19 meters per second. Right? And what that means also is that, well, we know the time scale is right there on the graph. It's struck here and then goes through its path here. So the whole thing takes 5 seconds from ground to the peak and then back to the ground again. So the first question, so if you're like, oh, okay, I think I kind of get that now, you need to pause and try to finish the problem from here, okay? How far does the golf ball travel? Well, in the horizontal direction, delta x is just equal to Vx times t. So that is 95 meters. Right? And then, that's part A, they are also asking us what is the maximum height above ground level attained by the ball? Well, what I know is that the speed, 31 meters per second, this is the speed at time 0, is equal to the square root, it's always equal to this, I'm going to call that Vi, right, because that would be the vertical velocity at time 0, plus Vx is constant, it's 19. So I think that I can figure out what the Vi is. It's going to be equal to the square root of that should have a name too. It's like not Pythagorizing, it's like I guess we're finding a leg. It's like legifying, maybe. Uh, 24.5 meters per second. And so now I think I have enough vertical information to figure out how high. How high is going to be the delta y. Would like to know that. Now I know my Vi. And at the highest point, the Vf is 0. Because it's the highest point. And actually, I know the time, too. So this is kind of overdetermined. I have plenty of information here. So what equation do you want to use? It's your choice. Anything with a delta y in it. 1/2 at squared plus Vit. I'm just going to use that one because, you know, I'm a big fan of the 1/2 at squared. So I've got negative 4.9 times 2.5 squared plus 24.5 times 2.5. And that is about 30.6 meters. And that is it.